29 of you have answered till now, which is approximately 51% of the participant. So I would request the other 50 to answer the question, if possible. We'll close the polls after 2 more minutes. Forty-one of you have answered the quiz, which is 74% of the participants. We are waiting for it to cross 85%. Forty-five of you have answered. We are closing the poll now. So I'll reveal the answers to the questions. First question is, what is liquid carbon pathways in plant? And the correct option is option A. And 36% of you have answered correctly that liquid carbon pathways is conversion of carbon to gas to liquid to solid, which is humus. So from CO2 to plant sugar to humus. Second question is approximately how much carbon moves through biological pathways each year. So the correct answer is option B, which and 28% of you have answered correctly, which is from 1,000 to lakh million metric ton each year. Third question is, what are the causes of formation of heat domes? So the options were change in ocean temperature, change in atmospheric pressure, change in climate change. So 72% of you have answered correctly that it is all of the above options. So this is the question which got maximum right answers. Last question was, what are the parameters that differentiate low soil and high soil aggregation? This was present in the last part of the module where they had clearly differentiated between the two with different parameters. So the first option was bulk density, second was rooting depth, third water shedding, which no one has answered surprisingly, uh, fourth soil pressure, and fifth was all of the above. So all of the above is the right answer, and 57% of you have answered it correctly. I hope this poll helped you refresh your memory of module 4 so we can have that state of mind to ask Walter questions. Vishy sir, if you have any comments, you can say them.
I think basically that reflects, our own understanding. I think we have to work on more sessions, and maybe this might not reflect actually, but it helps all of us to reflect again on the process, and maybe we have to improve more of our conversations, especially uh, post question and answers. I think the discussions we are having, I think we have to work on it, Diksha.
Yeah, sure, sir. So one of the important reflections that I've had during this week is we encourage the facilitators to ask questions and organize their internal meetings. So like Vishy sir previously stated, if facilitators are trying to initiate conversation, it's very important that you also participate in it because otherwise they'll get disencouraged. And if you have a discussion within your internal team out of breakout session, you'll be more familiar with each other. So the points that come through the breakout session and the question that we'll be posing to Walter will be much more refined, and we can utilize this 1 hour very efficiently. Apart from that, we have gotten module 5 as well. We'll be sharing it after the breakout session ends. And as Vishy sir has previously announced, the pre-work session will be conducted tomorrow. It won't be today, it will be conducted tomorrow. So I hope we have collected questions from all the participants. So throughout the week, I keep on telling the facilitators to pose questions and ask questions. So the maximum questions that are coming to us are from the facilitators, and less number of questions are coming from the participants who are not facilitators and co-facilitators. So I would ask you to pose questions so we can refine it and we can use that time efficiently. Apart from that, during the breakout session, I would request the co-facilitators to screen share because it becomes very difficult for a person to understand your points if nothing is given on the screen. Last time also I had reiterated it, so I hope this time it will happen and we screen share efficiently. So Walter is present with us. I would ask him to be promoted to the panelist.
And also, Diksha, I suggest that we are halfway through. We should also take feedback from participants on learning process itself. We've been sharing links. We've been conducting this process. If all of us feel there are mid-course corrections or mid-course changes, I think in terms of our approach to this learning, I think we should do it. We can in private sessions we can ask to give some feedback on ongoing sessions. Good morning, Walter. Welcome to the session. We request you to join us. Diksha, did you join?
So yes, he has joined. I think they are doing some technical checks on this.
Okay.
So till Walter joins us, can anyone give some feedback on the learning process? Hello,
Good
Walter,
morning,
can you
Walter.
hear us?
Yes. Can
Yeah,
you hear me?
yeah, we can hear
Can you
you,
hear me?
Walter.
Can you hear me?
Yes, Walter. Welcome to today's session. Hello, Diksha.
Yeah, he's muted his mic.
Okay.
Right. Is that better? Can you hear me now?
Yes, Walter, we can hear you.
Oh,
Welcome to
good.
the session.
Okay. And again, I don't have visuals at the moment. Normally, I have a screen of myself.
It's fine, Walter.
Okay. No, just leave it to you.
Yeah. And thank you very much for your sessions and insights. And we have been almost halfway through. We've been reflecting on the learning process and we're trying to learn for a period of time. And I invite you to this session. Thank you, Walter.
No, thank you very much. And vice versa. I mean, like, it's been very interesting for us to get the questions. Again, very grateful and impressed by the depth of your questions. So, no, that's very good. And I think, yes, these Q&As are valuable because they allow that interaction, that feedback, and giving you all a chance to then ask the questions that you see that are relevant. Often the answers are not always as precise. It depends on local situations, but that's part of the qualification. Like, it depends where you are, slightly different answers apply.
Walter, please continue.
Hello. Yeah. Okay. Start video. Yep. Now I have it. Yep. Excellent. Excellent. Right. Can you see my video?
Yes,
Yes,
Walter, we
Walter.
can see you.
Good. Okay. Excellent. So no, okay, I've got a couple minutes to go, but basically, yeah, whenever you're ready, we can get started. Yes, wonderful.
Walter, I would request you to give a summary of module 4 before we begin the Q&A in 5 minutes. Will
Yes,
that be
look,
okay?
thank you very much. And Diksha, that's exactly, I think that works well. I just briefly summarized what we're trying to get across in module 4, and then we come on to the questions specifically. I've got your questions here, of course, all relating to soil carbon and different aspects of microbial ecology there. And yeah, I mean, we'll go through them all, hopefully, and I'll try and be disciplined and go through them fast so we make sure we get through the whole lot. So you let me know when you're ready to start, right?
Yes, Walter, do you want me to ask the question straight away or will you give a
Oh, no,
synopsis of
look,
module 4?
let me, once we start, I'll give a synopsis for about 5-10 minutes, right, of the module 4 and what the objective, focus, and content was. And then, yes, then I'll be very grateful if you could go through and ask the questions, and I'll respond to each of them in turn. And as I said, hopefully get through them all in time.
I think we are waiting for Ben to join.
Aha, okay. I wasn't sure whether he would be able to join us today because of other commitments. So look, we might, if you like, just proceed or as we go. Once it's 3 o'clock here, right? Just to proceed. But it's more or less, it's more or less that now. So let's just get started, and then Ben will join if he can make it, right?
Yes.
Okay. Well, look. Greetings, everybody, and welcome now to this Q&A on Module 4. And basically, this is, of course, the Masterclass looking at natural farming in India. But more importantly, how do we understand the significance of natural farming and how we can extend it globally around the world and its significance in actually meeting the water, food, security needs of the future. The Masterclass started with actually a discussion of why natural farming is important. Then we looked at what we actually have to achieve, what are our specific practical ecological targets to achieve it, and then focused on, well, look, we have a solution, it's nature, and this is how nature created it. And in the fourth module, we very much looked at, well, how does nature do it? And it's very powerful because nature actually did it once successfully and used it over and over again all over the planet, all through the last 420 million years in creating and sustaining terrestrial ecosystems. And how nature actually functioned and did it was actually creating and regenerating the Earth's soil carbon sponge. And what's important about this is actually that one single thing: building, regenerating the Earth's soil carbon sponge is all that we need to do. And if we can do that as nature did successfully, then that solves and gives us all the solutions we need to cover the future. It gives us the water we need. It gives us biofertility. It ensures the nutritional integrity of our food that we grow, and thereby our preventative health. It gives us resilience from diseases and stress. It gives us productivity. And then it gives actually the sustainability of a green planet, of maintaining biosystems across all the land surfaces. And of course, that's extremely important in hydrologically cooling and stabilizing the climate. The last point will come back in module 8, 9, but really the last point is also critically important because it's regenerating the Earth's soil carbon sponge that allows us to sustain economic and social viability. It's the basis on which agriculture grew up, civilizations have grown, prospered, and survived. And of course, the key message is if we don't maintain that soil health, maintain that soil system, we end up with civilization collapsing. President Roosevelt made that very strong point in the 1930s in America, in their Dust Bowl. A nation that destroys its soils destroys itself. And all through human history, we've seen nations which have degraded their soils basically collapsing as a society, as an economy, and their landscapes aridifying. And really the whole history of civilizations have been really written in, have they maintained their soils, improved their soils, or degraded them? And what module 4 was all about is there's this one single thing that nature did. There's this one single thing that we must learn to do, and that's regenerating the soil carbon sponge. And we talked about it, and basically I've still got the little model here. It's a very simple thing, the sponge, or the concept. Instead of having a solid rock or solid compacted soil where all the mineral particles, as indicated by these little discs, all fused together and compacted, unavailable, creating the sponge really takes the same 10 little particles, 10 discs, and glues and joins them all together to create a loose, open, three-dimensional matrix And it's actually the physical structure of that matrix, which is the basis of the sponge and is the basis of soil function. Because once we've got this open three-dimensional matrix, we then have, of course, the capacity to infiltrate, retain, make available water. We have the surface area exposure of minerals, for example, these red discs. Excuse me. So we have the solubilization of minerals, enhancing biofertility. We have rootability, and with that, we build the resilience and productivity of that soil and the biosystems and the communities that depend upon it. So all that building the sponge is involving is, in fact, taking these mineral particles and simply rearranging them in this sort of configuration, an open lattice, and it's actually the air, the voids, the nothing that we've added to the soil that makes healthy soils. Okay, we've turned this into this simply by rearranging them. We haven't added anything. And so that's the secret of building soil carbon. It's zero input, but it's intelligently rebuilding these mineral matrices, lattices, which then give us the productivity. And basically, it's that simple and it's that universal everywhere, all over the planet, all through time. It's just been that one single thing of nature, building that sponge. And in a sense, that's what all the civilizations that have survived have done as well. Of course, East Asia, China, Japan, Korea, India, they were actually world leaders and were able to sustain high populations of hundreds of millions of people for thousands of years because of their wise management of their soils. And that's, in a sense, the challenge and the imperative that we have now to do that as well, to take what is now degraded soils because of our industrial agriculture, restore their structure through these natural processes, and in that way sustain their productivity, biofertility, hydrology, and the communities and economies that depend on that. Okay, so module 4 addressed that, and then module 4 looked at, well, what is it that we can do very simply and practically to build the sponge? And then we went through the simple logic of A, B, and C. And really, the logic says all we have to do is A, is agriculture, maximize photosynthesis, maximize plant growth, maximize, the fixation of solar energy, CO2, and water into sugars by the growth of green plants. And we do that very well in agriculture. But then what we have to do as well is very important. We've got to make sure that the biomass that we've created through agriculture, through photosynthesis, isn't lost rapidly by oxidation, by burning, which is a B. So rather than just fixing carbon, it's now very important that we don't oxidize that immediately back to CO2. And instead that we put a very significant portion of that into stable soil carbon, which is what we call C. Okay, so it's our management of our landscapes that governs the rate and the balance of oxidation burning and, of course, stable soil carbon fixation to build C. And it's really our land management practices that can influence that. And basically, to minimize the oxidation, to minimize the loss of carbon back to CO2, we have to change practices away from industrial agriculture and the clearing, cultivation, over-fertilization, biocides, bare fallows, burning that's associated with that, all of which rapidly moves moves biomass back into CO2. And instead of those oxidative practices, we've got to change and say, look, we have to microbially fix that biomass into humates and glomalins, stable soil carbon. We can do that through enhancing the microbial ecology of those soils and limiting those oxidative processes. And it's really there where we have the diversity of both industrial farming and natural farming. Industrial farming has been very much about maximizing oxidation, maximizing the extractive exploitation of soils, and natural farming, by contrast, is looking at building soil carbon through these microbial processes and limiting that oxidation. So we now have to go beyond industrial. We have to go beyond the green revolution and say, here is a new paradigm of maximizing carbon fixation in soils to rebuild the sponge, to rebuild, as we said, the hydrology, biofertility, etc., etc. And the simple process is A, B, and C, maximize growth, but then really minimize oxidative practices and enhance those microbial carbon fixation processes. And in a sense, we have full control both on A, B, and C. So it's us as individual farmers, as communities, urban agriculture, we control A, B, and C. And the wisdom is in now maximizing A, maximizing C, the fixation of stable soil carbon, and limiting how much is oxidized. And if we do that, then basically we can see innovative farmers all over the world are fixing up to 10 tons of carbon per hectare per annum through enhanced carbon practices, enhancing the C in their agricultural systems. By contrast, conventional industrial agriculture is still losing 5 to 10 tons of carbon per annum, per hectare per annum, turning it back into CO2. And of course, that's the symptom that we're seeing. That's the symptom we recognize, the increasing CO2 level in our atmosphere, and of course, the consequences in part for climate change. Okay, so it's really that oxidation which has been the symptom. And basically, instead of that oxidation, we have innovative farmers all over the planet using natural farming processes, fixing up to 10 tons of carbon per hectare per annum. The amount isn't actually so critical. What's critical wherever you are is that you're moving towards C rather than B. So even if you're only doing 3 tons or 4 tons, that's not the issue. The issue is that you're on that pathway. We then talk very briefly at the end of module 4 about the significance globally, because every year on the planet, there is a flux of carbon emissions, and there's a similar balancing flux of carbon drawdown. So basically, we are oxidizing carbon, and we're also, or we aren't, but plants are drawing it back down from the air into biomass. And that total flux, that total flow every year at the planet on the Earth is about 250 billion tons of carbon. So quite a lot, 250. And basically biology governs most of that, right? Most of that 250 billion ton flux is governed by our land management, how much we're respiring, oxidizing, using carbon to emit it, to generate CO2, but also how much our biosystems, soils are actually fixing it. At the moment, we are generating about 130 billion tons every year of emissions, and we're drawing down about 120 billion tons of carbon through plants. So that leaves us with a 10 billion tons carbon per year deficit, which is why CO2 is going up. And in a sense, the challenge is we've got to turn that around. We've got to get to negative net emissions, which means we've got to sort of basically pull down more carbon out of the air and put it back into soils where it came from than we are. By contrast, the whole global use of fossil fuels by humans is about 10 billion tons of carbon per year. So it's about 8% of this whole flux is driven by our fossil fuel use. So it puts it into context, into perspective, right? The whole fossil fuel emissions reduction story is 8% of the challenge, but the solution is in actually extra drawdown, extra photosynthesis, extra carbon biosequestration. And collectively across the planet, we can readily draw down an extra 20 billion tons. So that's twice our fossil fuel emissions. And that 20 billion tons will get us to negative net emissions, 10 billion tons of negative net emissions. And doing that will not just change the whole CO2 balance in the atmosphere, but most importantly, that 20 billion tons of extra carbon sequestered into our soils every year will rebuild their health, their structure, rebuild these matrices, rebuild their hydrology, biofertility, and healthy, viable biosystems. And of course, those healthy, viable biosystems is what's going to keep humanity surviving and prospering in equity and peace. So this is really module 4, the key, the key essential thing. I mean, it's our point of agency, rebuilding the Earth soil carbon sponge. And so we said, what is a sponge in this module? We talked about how do we grow it, A, B, C, and the significance of natural farming and getting to that 20 billion tons of net negative emissions. And it's all practical, it's all doable, and natural farming is really our key point of agency for doing that. So again, sorry for being a bit longer and recapturing what module 4 was addressing. But look, please now let's have a look at some of the questions that arose. Again, as before, I respect and understand the questions often go wider than just module 4. But let's look at each of the questions and then let me try and answer them. And hopefully that fills in some of the dialogue and some of the discussion. I'm very, very grateful and impressed with the quality of the questions that you're asking, because they're getting really to the heart of this whole understanding of natural farming and soil regenerative management. So over to the question, please.
Thank you, Walter, for that informative summary of Module 4. And you have rightly said that the nation that destroys its soil destroys itself, and land management is the way to go. With that, let me start with the first question. What is the contribution of paddy growing system in soil carbon sequestration, as there is low root proliferation, low biological activity, more soil compaction when compared to other cropping systems?
Right. Look, thank you very much. And yes, the paddy situation. And look, every situation has got its own characteristics. And certainly paddy, you're right, it has a lower root shoot ratio. The paddy doesn't have to put as much root biomass out because it's always got plenty of moisture. And so it can get the moisture it needs with fewer roots. And so it's putting slightly less carbon into the soil to explore that soil to access water and nutrients. And so, yes, there will be less biomass invested in the soil. Conversely, though, paddy soils, because they're anaerobic, they haven't got a very high oxygen level, naturally don't have very high oxidation rates. So whereas you're not putting as much A into the system, in the root component of the system, right? When you think you're fixing carbon, but less is going into the roots. But the fact is that the oxidation of those roots and those exudates is a lot less. And so you are still able to build good, healthy, organic soils. So, right, rather than having 100 units of root mass, you might only have 70 units of root mass, but because 90% of that root mass is staying in soil as stable soil carbon rather than getting oxidized, you can still end up with good humus formation compared to a plant which is producing, 100 units of root mass, but 50% of it was oxidizing because of the oxidative practice, which would only have, and again, 50 net units of carbon in the humate formation. So look, every situation you have to look at, it's basically this ratio of A to B to C. How much biomass am I producing? How much of that biomass is being oxidized? Can I minimize that? In paddies, yes, you can. And then how much of that carbon that is put into the roots and the root exudates is actually being turned into stable soil carbon through fungal activity, because it's only fungi that actually convert roots into humates, and it's only particularly fungi, the mycorrhizae, that take the root exudates and turn them into the mycelial networks, those fungal networks throughout the soils that end up making glomalin. And it's the humates and the glomalin that are long stable soil carbon sources in soils that last for 100 to 1,000 years and really end up giving the very good soil structure and the three-dimensional matrices that we're seeing in soil carbon. So every situation is different. There's no absolute correct, like in the sense of all soils will have some oxidation, but it's really the balance of B and C, the balance of oxidation versus carbon fixation, which become important. So I hope that helps answer that question. Next question, please.
Thank you, Walter. Next question. Explain about entombing effect, stabilization of microbial residue via interaction with soil minerals, and microbial carbon pump, their role in liquid carbon sequestration.
Okay, a complicated question, various parts to it. First of all, talking about my liquid carbon pump. Okay, so there's a lot of literature. My colleague Christine Jones has sort of raised that liquid carbon pathway discussion. And by that, she's meaning that, yes, plants produce sugars in their shoots, their green photosynthetic shoots, and up to 30-40% of those sugars are actually exuded or transported down into the roots and exuded out of the roots to feed the microbes. So the plants aren't just passive, they are actively feeding the microbes around their root systems, because those microbes are then critical in letting that plant access water and nutrients and colonize the soil. And the mycorrhizal fungi we talk about are a special group of microbes that have evolved very, very sophisticated symbioses or relationships with the plant roots. So they are actually using most of those root exudates, most of those sugars from the plants, to grow their hyphal networks. And of course, those extensive networks of fungal hyphae, up to 25,000 kilometers of fungal hyphae in a cubic meter of healthy soil, those extensive hyphal networks, when they die and they get replaced about every 8 days, leave behind a lot of organic detritus, which makes the glomalin, that makes the glues. And again, it's those glues that create the actual matrices, the sticking together, the aggregation of the soil. So the liquid carbon pathway is really the energy driver for structural soil formation by the microbes taking that liquid carbon, using it for its own food, and leaving behind the organic detritus, which then breaks down to make the glues that stick and make the aggregates work. Now, there was a question about the role of these microbes also in mineralizing and aggregating minerals. I'm not sure if I've got this part of the question correct, but certainly, basically, by creating the three-dimensional structures, you're actually exposing vast areas of mineral surfaces. The fungi are growing over these mineral surfaces in intimate contact, and so the availability of nutrients in that soil can increase greatly, not by more nutrients being added, but simply by the surface area of mineral available for nutrient uptake. So basically, yes, those microbes are helping to solubilize nutrients. Those microbes are also, of course, taking up those nutrients and so storing them in the soil in forms that they use and the plant can use. So it's limiting the leaching and the loss of nutrients from those soils. If you didn't have the fungi there, then and you didn't have the exudates and the fungi, then those minerals, yes, they would go into soil solution in part, but then risk being lost and leached from that soil. So the fungi are actually helping build up the mineral microbial pool from which the plants and the fungi can continually withdraw, use nutrients, and then, of course, store them back in there. So it's really like a bank, a reserve bank of mineral nutrients which become available, ever greater, increasing the bioproductivity, fertility of those soils. Okay, any next question?
Thank you, Walter. How has natural farming helped in accelerating the pedogenesis process in comparison to conventional farming?
Okay, now this is really the heart of it, isn't it? Pedogenesis is the formation of deep, well-structured soil, you know, both in terms of the three-dimensional structure. Again, we've got the little model, but also soils, you know, 1, 2, 3 meters deep, and those healthy soils, which of course govern the productivity. So that's what pedogenesis. And as we said, natural farming aids that enormously because, as we explained through A, B, and C, natural farming maximizes photosynthesis, but by limiting the oxidation of that sugar and enhancing the formation of stable soil carbon, the up to 10 tons of carbon per hectare per annum that the natural farming innovators are demonstrating, it's actually continually building healthier and healthier, more productive soils. By contrast, in industrial agriculture, what we invested in with the Green Revolution was very much based on extractive mining of the soils, of using basically plants as extractive vehicles. Can we actually take mineral nutrients from the soil and basically relying on then additions of more nutrients to replace those that we've extracted, but also using biocides, which effectively killed the fungal microbial ecology, that very critical biological life of the soil. And so then we were just using that soil as a dead, inert mineral medium which we were mining for available nutrients, but that we had to then add more nutrients back to replace. So natural farming is very positively building soil, aiding pedogenesis, whereas the industrial farming system was the reverse. It was basically oxidizing carbon from the soil. It was killing that microbial ecology that drives all these processes and progressively collapsing the structure of the soil, turning structured soils back to these compacted compacted rock-like soils with limited root growth, limited nutrient availability, limited water holding capacity. And so that's, in a sense, the reverse of pedogenesis. That's a degradation of soils. And of course, our industrial agriculture has been associated with the widespread degradation and destruction of soils. We have created over 5 billion hectares of land on this planet that is now basically desert and wasteland, arid wastelands. We've done that over 8,000 years, largely though over the last couple of hundred years of intensive agricultural, oxidative agriculture. There's only 14 billion hectares of ice-free land on this planet. So some 40% of our land, we have actually degraded and turned into man-made desert and wasteland. And of course, that's the process that industrial farming has driven. And that's the process that we have to reverse now rapidly with natural farming. Basically, we've got just decades to do that in, because otherwise we're not going to be able to hold the water, the biofertility, and sustain the food production to feed the 10 billion people projected by 2050. So it's really natural farming, restoring petagenesis, that is the critical point of agents that we have. If we do that, yes, we should be able to meet everybody's food needs, but we must embark on that rapidly, because obviously that's a massive challenge, but only restoring the healthy soils of this planet can achieve it. Okay, next question.
Are C4 plants such as amaranthus more efficient in carbon sequestration as compared to their C3 counterparts?
Okay, very good question. Yeah, okay. C3 and C4 plants, right? Now, obviously, the C3 and C4 diversity in plants relates to their photosynthetic activity, right? So C4 plants, of course, are more productive in tropical environments, in warm, tropical, moist environments, and can be more, higher yielding, whereas C3 plants are much more adapted to grow longer in more temperate, cooler climates. But both of them produce both of them are producing photosynthate. And so from a soil carbon point of view, it doesn't really matter whether you've got a C3 plant or a C4 plant, right? As long as that plant is maximizing its photosynthesis production, its sugar production, the exudates, the liquid exudates going to the roots, the root mass, then what matters is how much of that that photosynthetic material, is being either oxidized to CO2, which is what we talk with B, that's the burning, or whether how much of it is turned into stable soil carbon. So natural farming is really focused on, the difference between B and C, the ratio of oxidation versus stable soil carbon formation. And as we said, that's governed by our practices, how much we've got oxidative industrial agricultural practice or natural farming practice. The difference between C3 and C4 plants are just two variants in fixing carbon from the air in the first place. But no, they don't actually significantly influence the B and C ratio or the oxidation, because that's governed by our soil practices. Now, it's fair comment to say wherever you are, you're trying to optimize the system where you're maximizing photosynthesis, minimizing oxidation, optimizing carbon sequestration. Okay, so for amaranth, you'd be looking at how do I optimize that in each location, but you'd be doing exactly the same optimization processes if you were going through C3 plants, more suited for different climates. So, an important point in terms of but not really a key determinant whether you're fixing carbon in soil or not. Okay, next question.
I would request Dr. Pushpa to ask the next question.
Good morning, all. My question is, regarding the microbiology. Since from 1980, a lot of development was happened in microbiological studies as well as a lot of microorganisms we were identified. Why soil microbiology, only very less amount of microorganisms were identified? Still, we have so much of technology, DNA analysis, sequences, so much of technology was developed. Why it was become complex, so complex? As per me, one idea I have is metagenomics. So is there any idea, other reasons were there for these microbial identifications? Why it was not happening? That is my
Yeah.
question, Walter.
No, and it's a very, very deep and wise and important question, isn't it? Okay, well, yes, let me try and keep it very simple. What's happened in the 1980s, we got very sophisticated in starting to look at the genomics of soils. You know, what is the DNA of soils? And we were able to then look at, okay, here are all the different nucleotides from the different DNAs of the different organisms. And we were able to confirm what we already knew, that, listen, there are billions of organisms in the soil, right? And we've only ever actually been able to identify perhaps 1 or 2% of them. And so, in fact, there's a vast diversity of organisms in soil that we never knew about, and we still don't know about, except we know now from the DNA record, yes, there's vast quantities. And so microbiology, in a sense, we're not going to be able to understand it by looking at each organism or even counting how many organisms or how many bacteria or how many fungi. You know, there's just a vast diversity, and we've only ever looked at a small percentage of that. And what, in a sense, functional microbiology has been really more important, as rather than counting the numbers and trying to stamp collect, you know, allocate them all to species and what have you, we've been really much more interested in looking at the functional roles of the different groups of organisms. And see, that becomes quite simple, but much more powerful than if we look at the functional role of organisms per se, rather than which species is doing what. So if we look at, for example, in terms of, and this we'll do this in module 5, we look at this in terms of hydrology, then what is the role of microbial ecology in making soil hydrology, allowing soil structures, infiltration, retention, availability of water, you know, metabolic water, all the different ways that microbes influence the hydrology of soils. So, see, rather than looking at what species and getting lost in literally the billions of organisms, we're saying, what is this hydrological function and how do we enhance that hydrological function? The same applies with biofertility. We'll talk about that in module 6. You see, there are 5 cardinal processes governing nutrient availability. It's the fixation of nutrients, the solubilization, the access, uptake, and cycling of nutrients. So these become the real principal functional things governing biofertility. And it doesn't really matter which organism is doing what, because we don't even know all of that, but we know these 5 functional processes. Yes, we can actually improve soils and manage biofertility. So to answer your question, yeah, from the 1980s, we've got ever more sophisticated, more and more academic, and basically we're identifying more and more organisms. Literally, there's billions of organisms in a gram of healthy soil, and they've got an enormous diversity and, of course, an enormous DNA range. And yeah, we can take that DNA and we can look at all the nucleotides, and we look at a bowl, I mean, the equivalent of a bowl of alphabet soup. You know, we see all the different codes, but we have no idea what they mean, where they come from. And so really functional microbiology, practical microbiology is much more looking at these functional roles that microbes play. And so, yeah, we've now, in a sense, got ourselves lost a little bit in lots of detail, lots of genomic work, but it doesn't always relate straight back to, well, what are the challenges and the solutions and the action points that we need to do. I think in our natural farming discussion, there's no harm in having information, of course, but we always want to focus more back on what are the critical functional roles, what is the health of those roles, rather than what are all the different organisms contributing to it. I mean, like if you look at things like B, like the oxidation of biomass in soils, the microbial breakdown of sugars and cellulose, there's literally thousands of organisms that have enzymes that contribute to that. So we don't need to know every one of the 1,000, but it is valuable to know the total rate at which those sugars are being broken down, to give you a measure of B, for example. So that's what we're getting at, is the actual process functional rates, rather than looking at the detail of what are the organisms involved. But I agree, microbiology has to get back to looking at, yes, what is the roles that these things are playing, rather than here's all the detail from an organism point of view. Even now, with all this genomics, we know less than, we don't understand more than 1% to 2% of the total microbial population. And so all we can really say, there's more that we don't know, but we can make progress enormously by understanding these functional roles of microbes. I hope that sort of helps answer. It's not always a perfect answer, but it does hopefully address some of the confusion there.
I understood, Walter. Thank you so much.
I would request Achyutan to ask the next question.
Good morning, Walter. So my doubt was, how was the soil sponge formation different from like a normal condition and a wetland ecosystem? Because obviously the nothingness is, in this case, is filled with water, and the exudates can't stay in that rhizospheric zone. So apart from the microbial changes like methanogenetic bacteria and all those things, what is the major difference, and how this soil sponge formation differs from the conventional?
Yeah, look, could you just, I didn't get all of that question. I think could you just repeat, what was the key thing you want to know? Please ask it again.
Like, how does this sponge ecosystem, to say on a whole, differs from that of a upland system, the wetland ecosystem?
Yeah, look, actually, I'm reading the transcript, and I think I might be getting confused here. So, okay. So basically, could you just bring it down again? Just tell me again what I'm not getting the guts of what you're asking. Yeah.
Okay, the soil sponge formation.
Yes.
In wetland ecosystem, how does it differ from normal ecosystem, normal sponge formation?
Okay. Well, no. Okay. Right. So thank you, and it's important. The sponge, as we're seeing in our little thing, the sponge is normal soil formation. You see, normally we've just got a mineral soil, and it's just bits of mineral detritus, right? And it just is there as a compacted aggregate, but it's all, compacted, doesn't hold much water, can't infiltrate, very limited nutrient surface exposure. So it's there as a dense, compacted, matrix. And all the sponge is doing is actually rearranging those same particles to make it into a three-dimensional lattice. And all the sponge does in rearranging it and just joining it, gluing it together in these random ways is just to add a lot of voids, a lot of space. Okay, so if you look at the bulk density of a healthy soil, it's about 1.2 grams per cc. And if you look at a compacted soil, it might be 2 grams per cc. So you can immediately say there's 50% up to 50% air in a healthy soil. And so basically that's what basically the sponge is doing. It is just creating voids and air, but it's also creating the surface exposure and the ability of those nutrients to be available in that soil to hold water. And so that's the normal formation of petagenesis, and it applies in all situations. Now, basically, obviously when the soils are wet, when they're waterlogged, then those voids aren't there, but there's still water holding capacity. And so, yeah, I mean, okay, so I'm not sure if that is answering what you're asking, but certainly that soil can hold water, and basically make available water, make available nutrients at a much higher level than that exactly the same mineral soil, while it was in a sense compacted but not effectively available. But perhaps, Diksha, could you perhaps also rephrase the question if I haven't understood exactly what was being asked?
Sure, Walter. So the question basically asked, how does soil carbon sequestration and soil sponge formation work in wetland ecosystem, and how is it different from an upland ecosystem? And I think you answered the question.
Okay. So how does it work differently in a wetland compared to a dry land situation? Okay, so I didn't get that part. Well, look, basically, the sponge is the same in either case, right? So basically, while the soil is in a drained situation, it's forming the sponge, the humates, everything forms the same. I suppose when it's in a wetland situation, there's a lot less oxygen in that soil. So as we said, in the paddy soil, there's less carbon oxidation, but they also can get to a point where there's less microbial activity because, of course, the microbes need oxygen, or the aerobic microbes need oxygen in that soil. So if you then make it very wet, continually wet, then it can become anaerobic, less oxygen, and therefore you get lowering or different microbial activities compared to a well-drained dry land soil. And then you've got to look at, again, relating back to the next question, where you have things, for example, like nutrient availability, these 5 functions of fixation, solubilization, etc. Then you ask yourself, well, what are the activity of those processes under very wet conditions compared to dry conditions? And that would vary. You also end up risking sort of toxicities happening, like basically under some wetland anaerobic conditions, you can get more toxic items coming. But yeah, a whole range of different chemical, physical environments are created depending if it's in wet or dry. I suppose the sponge is very important in the sense the sponge does allow soils to drain. Whereas once we have compacted soils, and we do this under industrial agriculture, then we end up with waterlogged, wet soils which can't drain, and then they become, in a sense, less and less productive because they're anaerobic and haven't got, the bioproductivity that they would otherwise have. So I hope that's sort of answered. I'm not quite sure if it's perfect, the
Yes,
answer,
Walter,
but
thank
I
you.
hope
That
that has
answers
helped.
a lot of my questions. Thank you.
Thank you. Yeah.
Thank you, Walter, for addressing so many questions in a limited amount of time. And the next question would be the last.
Yes, and please let's keep. Yeah. Okay. Thank you.
Next question would be the last question for module 4. Dr. Muniraja, can you ask the last question?
Yes, madam. Yes, madam. Sir, good morning, sir. Water will convert from the liquid to vapor state in the process of transpiration by the plants and evaporation by the oceans. So nearly 71% of planet occupied by the water and the rest of the 29% by the land, including agricultural fields. So which one is
Yes.
the major role in the cooling effect process in the planet?
Right. Okay. Yes. Thank you very much. Now, obviously, yes, 71% of the planet is covered with oceans. 29% of the planet is covered by land. And so basically, obviously, there's already oceans are a dominant sort of pattern. I must make the other point to start with that, yeah, 95% of the heat dynamics of Earth is governed by hydrological processes, right? The CO2 component of the greenhouse effect drives about 3.8% of the planet's heat dynamics. So by no question, hydrology, water is the dominant heat mechanism. And now the question is, all right, what role do oceans versus land play in this? And it depends really what you're looking at. If you're looking at heat absorption, then there's no question the oceans in the long run absorbing a lot more heat. 93% of the extra heat being retained by the planet, and because of the whole global warming, disruption and greenhouse effect is actually being absorbed by the Earth's oceans. So we're slowly heating the Earth's oceans, but there's such vast volumes of it that it's going to take a long time both to basically heat it up, but also then once it's heated up, the long-term consequence of that heating. In terms of the land area, obviously it's only 29% of the area, but basically the land area has also been able to evolve plants living there. And the leaf area of plants, this is called the leaf area index, can be up to 10 times the surface area. So you can think of a forest, and there's a square meter of forest, but it may be sustaining up to square meter of land. And so whereas the ocean is in a sense a two-dimensional surface, right? Air, liquid. And so you've got a two-dimensional surface. On the land, you can have a 10-fold dimensional surface. So if you think of leaves, for example, transpiring water into the air, per unit area, they can be up to 10 times more than a flat body of water. Now, obviously, that doesn't occur everywhere, but what that's saying is that basically transpiration or plants transpiring liquid can actually do it, even though they haven't got the same area as the ocean, they can do it just as well. The other thing, basically, in terms of cooling the planet is that, yeah, we now look at the processes of cooling. And obviously, plants are taking up water from the soil, transpiring that into the air. And to do that, the plant has to turn that that water from liquid to gas. And to do that, it needs to have latent heat of vaporization. It needs to have energy from the surface to turn it from a liquid to a gas. That's some 590 calories for every gram of water transpired. And so through that process, as plants uniquely have an enormous impact in naturally cooling the surface. And you can understand in a forest with 10 times the leaf area compared to its surface area, can be significantly cooler because of this transpiration effect. Okay, so basically, yes, 71% is ocean, 29% is land. Yes, 95% of the total heat dynamics is governed by water. But then if we look at individual processes, for example, transpiration, then yes, the land can compensate for some of that lower area by higher leaf areas. That evaporation transpiration effect actually takes some 24% of the incident solar radiation we get from the sun and takes it from the surface back up into the upper atmosphere and then largely out to space. So it's not an insignificant cooling effect. It's really a key part of the Earth's natural air conditioning effect. So the power of vegetation, leaves in this natural cooling is very important. There's other processes we won't go in this answer to this question, but there's other processes, not just transpiration. The other point I'd like to make, though, is that we have got a human crisis, climate change. We need to do something about it. We need to actually directly, safely, naturally cool the planet within decades, because certainly the oceans are heating up and basically we have very little chance to influence that. You know, we don't have agency over the oceans, and certainly greenhouse gases are going up. Well, we can have agency over that by emission reductions, but the biggest point of agencies we humans have in naturally cooling the planet safely and in time is through actually revegetating, rebuilding this transpiration, this green move on the transpiration of water from green tissue. So we're taking heat from and then largely out to space. So when we're looking at natural cooling, it's really a question also, where do we have agency? Where can we influence the natural process? This transpiration is, of course, critically important. But perhaps more important, or sorry, perhaps equally important or more important even, is what, in a sense, you've been demonstrating in India. Because Vijay and through pre-monsoon dry seeding, we formerly arid areas, dry, and by putting plant
We will wait for Walter to join again. I think there was some internet issue. Ben, can Walter join the call again?
I can see Walter's connection is struggling here from through the WhatsApp connection. So I think it might be good to either carry on with some other program or to complete. I think he's possibly dropped out.
Sure, Ben.
Thank you, Ben. I think today's session primarily again focused on revisiting Module 4. what Walter has been reiterating from the module 1 is how natural farming is offering solution for some of the challenges we face. And then he is explaining 3D structure, how to build the sponge, right? And he's giving ABC
So
model where,
Dr. Walter joined the call again.
okay.
Hello. Hello. Hi.
Hello,
Welcome,
Walter.
welcome. Hello, Walter, please.
Okay.
We're
Right.
trying to recap, yeah.
Apologize. I mean, I don't know what happened. I just, the dropped out, like I was, interrupted and somehow dropped out. Can you hear me again?
Yes, Walter, we can hear you. Thank you.
Good. And we're just finishing off that discussion about heating the planet, and we're just talking about pre-monsoon dry seeding. And just to finish that answer, it's very important in a sense that basically this innovation of pre-monsoon dry seeding and its capacity to regreen what had previously been arid rangelands or degraded arid lands, this can actually profoundly contribute to cooling the planet, because the physics of re-radiation on the planet, it's governed by the amount of the soil temperatures, right? The soil temperature is critically important in governing how much re-radiation is coming off the planet. And if we can keep those soils protected, moist, green, vegetated, then they will re-radiate massively less heat back into the air compared to if we've got bare, red, degraded land that's absorbing incident solar radiation. So it's really our capacity to keep landscapes green, protected, covered 365 days of the year that has an enormous effect on how much re-radiation comes back from those land surfaces. And of course, it's that re-radiation of that heat which is a driver of the greenhouse effect. Okay, the greenhouse effect is very simply a matter of how much is re-radiated and then what percentage of that re-radiated heat is absorbed by greenhouse gas molecules in the air. And by keeping land surfaces protected, moist, vegetated, cooler, we can actually turn down the actual re-radiation which drives the greenhouse effect. We can do that irrespective of the greenhouse gases in the air. And so now, because we've increased CO2 concentration, it'll take centuries or millennia for dropping them down. This actually direct hydrological cooling options through pre-monsoon dry seeding becomes actually one of humanity's only tools to safely, naturally cool the planet in time. So it's actually quite profound. It warrants a much more detailed discussion, the physics of it, but also the practical extension of it, because the question is what sort of area of that 5 billion hectares of man-made desert and wasteland would we need to regreen, to put a protective cover on, to actually drop the re-radiation enough to give us a cooling offset to the warming that we've otherwise locked in. So very important question. Thank you very much. And I apologize for the disruption in the answer.
No problem, Walter. Thank you so much for answering so many questions from Module 4. We had a very informative and interactive session. These sessions are enabling a lot of learning for us, not just at grassroots level, but also in the global context. I would also like to thank Ben for putting up so many informative materials in the chat box. I would request participants to go through it because they are very useful. We will continue our discussions on Module 4 in breakout session, and we'll discuss the application of Module 4 at the grassroots level. Thank you, Walter, so much for the session. And if you have any concluding remarks, please.
Yes, thank you. Thank you very much. And sorry again for the disruption. And yes, as we go into Module 5, 6, and 7, we'll be looking at the sponge, but now how does it specifically enable us to manage hydrology, biofertility, and the nutritional integrity of our food. And yeah, the agency the sponge gives us in getting these critical outcomes for humanity's future. So thank you very much and look forward to module 5 next week.
Thank you, Walter. Vishwi sir, if you have any remarks.
No, I don't have. Only thing is that we keep reinforcing this fact, all the 4 modules, to stop oxidizing what we actually produce on Earth. And we've been doing for a while, he's quoting examples of Korea, Japan, and India. And basically, the fundamentals, what he's trying to drive us, giving this example, is very important for us to revisit again and again. And also to change the narrative, what we have in mainstream media, what we get to hear this, whole 8% fossil fuel is just not the challenge. And natural farming offers a bigger solution, and he's trying to understand the bigger picture of it in terms of its impact. And what is happening is irreversible, but we can reverse it provided we understand this basic fundamental aspect of natural farming. Thank you, Walter, for your wonderful sessions.
Thank you very much, and look forward to the ongoing discussions. Thank you.
Yeah, thank you.
Okay, all the very best. Thank you.
Yes,
Bye-bye.
thank you.
Bye, Walter. I would request the participants to join the breakout sessions. The link for the breakout session is in the main WhatsApp group. So you need to leave this call to join the session. Bye, Walter.